All right, now let's talk a little bit about what happens with power. At the end of the day, we are only building transmission lines to transfer power from one location to another. And so it's very important for us to use the knowledge we have now for voltage and current to understand what happens with power. We are basically dealing with the lossless case so far. So we are assuming that power is not lost in the transmission line. And so let us look now at the power. So first I have written here the incident power in the transmission line, which is the power that the incident wave carries towards the load. So we know from basic knowledge of circuits that this can be found simply by multiplying the incident voltage with a complex conjugate of the incident current and then divide by 2. Here I'm assuming, of course, that I'm talking about amplitudes and not RMS values. If we were talking about RMS, that 2 would have gone away. So I have simply expressed here the knowledge I have for the incident voltage. I have simply expressed here the incident current, complex conjugate, and that gives me this interesting and famous result that the incident power is going to be nothing else but V naught square magnitude, V naught plus square magnitude, divided by 2 Z naught. And again, that 2 would not have been there if you had RMS values. Here I have magnitude values, so that 2 is actually there. Similarly, I can actually find out the power reflected from the load. In other words, this is the power that the reflected wave moves away from the load. The reflected wave has a magnitude of V naught minus, and so if I basically plug in exactly the same expressions as I had before, where I simply replace V naught plus with V naught minus, I will get the expression that you see right here. So in other words, the reflected power will be equal to V naught minus square magnitude divided by 2 Z naught. Of course, I do know that the magnitude of V naught minus is equal to gamma L magnitude times V naught plus magnitude. And so by using this expression, I can find out the reflected power as a function of both gamma L and my incident power, which is this guy right here. So that gives me to the equation that you see right here, which is an incredibly intuitive, incredibly beautiful equation that allows you to very quickly express the reflected power as a function of your incident power times gamma L square magnitude. That should be really the main argument of what I mentioned before, that gamma L for passive loads magnitude has to be between 0 and 1. And I'm putting here the equal signs too to cover the extreme cases as well of 0 and 1. But in reality, every time you know the magnitude of gamma L, you can very quickly find out how much is the reflected power that you're having. For example, in the example I just covered, gamma L had a magnitude of 0.5. That means that in this example, 25% of the incident power were actually reflected back to the load. So if I have some incident power from my incident wave, and I have some reflected power from my reflected wave, what is the total power that actually the load will consume? So the total power that the load will consume can simply be found by subtracting the reflected power from the incident power. So P incident minus P reflected will actually give me the result that you see here. Or if I write it slightly differently as a function of the incident power, then I have this other very interesting, very intuitive equation that gives me the power of the load as a function of the incident power and again gamma L. So the main thing that you should remember here is that the voltage and current calculations are really done because we care about power. That's the number one thing that matters in transmission lines. This is the number one thing that matters in RF circuits. This is the number one thing that matters in real life anyways. Everybody cares about power and energy. That's what you pay for, whether you consume it or whether you produce it. So really, we should worry about finding the incident power when you know the waves, the reflected power when you know the waves, and the power that finally the load will consume.